This is a video covering an assembly language that can be used with my Relay computer. And it forms part of a 2020 update series of videos. This is the third in the series, and the first one looked at the architecture of my Relay computer, and then that was followed by a look at the instruction set. This video continues on looking at an assembly language that makes it easy to program the computer, and then next time we'll look at an example of programming the computer, and then I'll move on to a tour of the computer followed by a demo. As mentioned in the first video, we looked at the architecture, and on the left here is the diagram that came out of that. This shows all the functional working parts of the computer. On the right is what came out of the second video, and this is the instruction set for the computer. Each one of these binary opcodes tells the computer exactly what to operate and in which order. So in the case of the first instruction, the move 8, we can tell it to copy a value from one register to another. For the third line, ALU, we can ask it then to take the value in B and C register and add them together, increment, or perform a number of logic operations. So if we were to make a program from all of these, what would it look like? Well, here's an example. Can you tell what it does? No, me neither, and I wrote it. So the problem here is that actually this makes perfect sense to the computer, but it's not particularly human friendly. It's quite difficult to read, and it'd be even harder if you need to debug it or maintain it over time. So what can we do instead? Well, this is where higher level languages come in. So in this case, here's an example of an assembly language. Now on each line of the program, rather than a load of bits to specify an opcode, here we have what's known as a mnemonic. This is just a handy way of remembering one of those opcodes. Now hopefully you'll agree here it's much easier to read and understand what the program is doing. Now you can take this a level further and go for an even higher level language. So in this case, if we looked at an example that's written in a C type language, this particular case it's a C# language. Here now it's even easier to understand exactly what's going on, but as you can see now you're starting to get a little bit more abstracted away from the way the computer works. So if we concentrate on the fourth line of the program at the right, that actually has a direct relationship with the lines in the middle. And this is quite typical for a very high level language program, in that there'll need to be a process called compilation that will convert the line that tells the computer what you would like it to do into actually how it needs to go about doing that. So the code in the middle here actually is how the computer itself would have to do the multiplication, in this case by repeated addition. But the code on the right just says multiply it. But our computer can't do multiplication, so there needs to be something in between those two that will convert from the high level language into a lower level language. Now what's interesting for the assembly mnemonics is they typically have a one-to-one relationship with the opcodes. So when we're working in assembly, we really are working at the lower level of the computer. We're dealing with the computer at the hardware level, but it makes it just much easier to remember and much easier to write programs. So this is why I've chosen to use an assembly type language for this computer. And what we'll need to do, of course, is when we actually write a program in assembler, we'll have to hand convert it into the opcodes because that's what the computer actually works on. Now eventually we can automate this by actually making an assembler which will do all this for us, but that's something for another day. Now actually interestingly, I probably will end up writing a C# type language and write my own compiler, so you could actually then do it in a high level language and it would work out all these individual stages for you. But again, that's definitely something for the future. Right, okay, well let's run through the available mnemonics, and as mentioned before, these will all have a direct opcode relationship, so as we go through this we'll refer to the opcodes. So let's start with moving values between registers. Here's the opcode, and in each case I'll pop the opcode down in the bottom right along with the class of instruction that it represents. So in this case we're looking at the move 8 class of instructions, and they take 8 cycles to complete. So the mnemonic we're going to use here is move, M-O-V. Now actually the assembly I'm using here is kind of a mishmash of many different types out there, and many have different conventions for the way they do the mnemonics. I've kind of just gone for the ones that appeal to me aesthetically. Move is a very common one though, very common in most of the assembly languages. And the way this works is you give it a source register and then give it a destination register. Now to help with these, I'll create a railroad diagram for each of them, and here's the one for the move. So this helps you see basically what the options are. So in here, you give it a move. You can then choose between the A, B, C or D register as your destination. You then give a comma, and then you can put your source register as an A, B, C or D. So some worked examples of that look like this. So in the first case, we're setting A from the value in B, then we're setting the value in C from the value in D, and the last one we're setting d to the value of d. Now in all cases here I've added the opcode that these represent, and I say there is a direct one-to-one relationship between each of these. Now the last one's an interesting case. So the a equals b and c equals d is fair enough, but what about the d equals d? Well, we know at a hardware level that'll actually just wipe that value out. So move is okay, that will work, but it kind of relies on you knowing that that will wipe the value. It might not necessarily be what you expect. So what we can do is add a synonym here. And in this case, it's CLR, clear, which is just a handier way of saying clear that register down. So in the example here, we've got CLRD, which is basically equivalent to move D, D. It's just another way of saying the exact same thing. You can see in both cases the opcode that it produces, the 000-11011, is identical. So as far as the computer's concerned, they're exactly the same. It's more just for our benefit than anything. What I'll do, as in the previous video, is I'll keep tally of the mnemonics we're creating as we're going along. So you can see at the bottom right here now we've added the move and the clear to our list of mnemonics. Now you can see from the number of gaps there, that's the amount of mnemonics we're going to end up with. There's actually not a huge amount of them, which is useful because then it makes them easy to remember. Now again, there's a few ways of going on this. You can either have loads of mnemonics or you can just have a few. In my case, we're just having a few. Next up then, let's look at the 8-bit load immediate, which allows you to load a value between -16 and +15 into either register A or B. Here's the opcode again from last time. It's a set AB class and it lasts 8 cycles. The mnemonic equivalent here is going to be LDI for load immediate, and it takes 2 parameters, a destination and a value. Here's a railroad for it. And here's some examples. So these all kind of work as you would expect. Just remembering again that the last 5 bits of the opcode that they produce is the binary equivalent, but also that is extended by signs. So if we've got, say for example, of loading -1 into B, the penultimate one there, you can see that it's basically all the ones. And if you remember from the last video, the way this works, that in this case, if you had 0, 1, 1, 0, 1, it would extend the 0 all the way to the left. And if you've got a 1 at the left, it'll extend the 1 all the way to the left. This is why just having 1, 1, 1, 1, 1 will actually result in a -1 because it extends the 1 bit all the way to the left. And now here I'm actually loading the value. I'm representing the value as just an integer. But of course, there's no reason why I couldn't do that in binary form or in hexadecimal form. I think for me it just made more sense to just keep this as integers because normally it'll always be a small value you're loading in. But the key thing again is it's all about how it's converted into an opcode. So even though we're using integers here as a base 10 number, it still results in the same opcode. So it's all just about how we want to define the assembly. And this is the beauty of this. You can really design the assembly just the way you want it and just the way you like it to look. So we'll add that to the list. That's LDI. And we'll move on now to the arithmetic operations, part of the ALU operations. So again, ALU class of instruction and 8 cycles long. And the 2 arithmetic operations we need is the add and increment, 2 things the ALU can do. So the mnemonics are add and inc. And I note here now we've got an option, so we can optionally tell it a destination, or we can just let it assume what the destination should be. Here's the railroad for that. So if we don't specify it, it'll assume to be the A register, because normally most operations will be going to the A register. If we want to go to D, we have to specify that, and we could optionally specify to do the A register, but of course that's equivalent just to not mentioning it at all. Here's some examples then. So the first one will add B and C together and put the result into A. The second one will add B and C together and put the result into D. Same for the increments. So in this case, we've got increment and we're going to set B plus 1 into A. And the second one, we're just making that A explicit. So you can see there the opcode's identical in both cases. Again, the computer really doesn't care. It's just there for our convenience. Now, I showed it in the last video, but here's the truth table for how the adds work. So again, you've got the B and C inputs, and then you've got the carry in, and then you've got the result coming out, along with a carry out. So as a worked example, here's adding 2 numbers together, and in this case, it's 2 numbers together that will actually create a carry out. So just bear in mind that would set the carry flag in the ALU condition registers. And here's an example of increasing a value, which only operates on B. So here it's B effectively plus 1. If you want any more information on these, probably worth looking at my previous video, which was around the instructions. That goes into a little bit more depth about how these work. So continuing on, let's look at the logic side of the ALU. Still the exact same opcode. And what we'll do first of all, we'll start with just the 3 main logic operations, which is the AND, OR, and exclusive OR. And here's the truth tables for those, as we'd expect. Now again, the mnemonics here are quite interesting because what I'm trying to do is try and keep these sort of 3 letters. So OR is a little bit weird because I've just stuck an extra R in there just for good measure. The exclusive OR is interesting because you can go for XOR or you could go for EOR as exclusive OR. And I've just gone with EOR because the assembler that I've generally been copying from or generally been nicking mnemonics from tends to go that way and it just looked nicer to me. But again, you could go either way on this. It really is up to the designer of the language. Now there is something interesting with the XOR or the EOR as it were here, and this is basically where you can use it to compare values. If both values in B and C are 0 at each bit, or if both values are 1 at each bit, the result will be 0. It's only when the values are different from each other where you'll get a 1. And that means across the board, if you compare 2 values by using XOR, if they are identical on each bit, the result will be 0. And if they're not identical, the result will be something other than 0. And we can use this when doing comparisons. It's a very quick thing to do. So what I'm going to do here is introduce a synonym for EOR called CMP for compare. Now again, these do the exact same thing. It's just that compare is sometimes more useful if you think, well, I just want to compare these numbers together and actually it's going to be done by an XOR. And when you specifically want to do an XOR, you can just use the EOR command. So we're going to end up in exactly the same thing, and it's just there for convenience. We've got 2 more logic functions to add then, and that is the NOT and the rotate left. So we'll add those on there as well. And again, the truth tables for those are quite straightforward. So NOT is just basically if it's on, the answer is it's off, and if it's off, it's on. So the rotate left, again, I've put down here is shift left, but really it is rotate left because what the bit on the left-hand side will rotate back and come in on the right-hand side. So again, you saw that in the last video, but we'll use ROL as for rotate left rather than SHL for shift left because they are different things. You could say that shift left would lose the value on the end and just bring in zeros on the right, but really this does rotate the values around. So let's get a look at the railroad for this. So here's all the values. You can see there that the EOR and compare, I've just tried to pick them out as being more or less the same thing. So they look slightly different in the railroad. And again, the destination, you can optionally specify that. If you don't, it will be assumed to be the A register. Here's some worked examples of those. So we've got an AND going specifically to D, an OR, an exclusive OR, a NOT, and a rotate left. And again, on the right, you can see then you've got the opcode for each of these. And again, the last 3 bits are the function that we want. And the 4th bit in from the right is the destination we're going to. So most of those are 0 because it's going to A. The one that's going to D has that bit set to 1. So let's pop that in the list on the right. And you can now see we've covered off quite a bit of our list of mnemonics. A note here that the base of the first column is all the AOU operations. And so there'll be 9 in total of those. Right, let's move on again. So now branching. So far with the instructions we've got, we can make a linear program that just does one operation after another. But what's really important is the ability to be able to go to other parts of the program, perform loops, and also perform decisions. The opcode from last time is as follows, and this is a go-to class of instruction and takes 24 cycles. So again, it's one of the longest instructions we've got. Again, the opcode we introduced in my last video, but basically it starts with a 1-1, and then we have the destination, M or J. We have whether we want to jump on the sign bit being set, the carry, the 0, the not 0, and then finally the last one then just optionally loads the XY register with the address of the next instruction before taking that jump. So let's look at the basic jumps first. So we'll have a jump and a jump subroutine. And these are both unconditional jumps. They'll always jump regardless. And the only difference here is that the subroutine will save that XY value first before taking the jump, so we can come back to it later on, whereas the unconditional one doesn't bother with that. The difference, of course, is just in the very last bit, because it's the X flag that we're setting differently. So here's an example. Now, again, for convenience here, we don't want to have to work out exactly what the address is, so we use labels here. So in this first line here, this will jump unconditionally back to that location in memory. Now, actually, this program will just loop it as an infinite loop, because each time it jumps, it will jump back to the exact same instruction, but you get the idea. Now, it's worth mentioning here, of course, that if we're actually going to convert our assembly program into the machine code, we'd have to then replace all these labels with the actual address of where that line would appear in the program. And again, that's where when we start automating that, that'll become much easier for us. But in my next video, where I demonstrate doing some programming, you'll see how this is all done by hand, so you get an idea of how it all works. Right, so let's add that to the list on the right, which is going to be all our branching instructions. So what else can we do with branching? Well, we've done the unconditional jumps, now how about the conditional ones? So here's a list of the ones we've chosen to go with. Now actually there's quite a few permutations here, so I've only selected a subset of them. So the first one is branch not equal. So that basically means if the result of the last ALU operation was not equal to 0. In other words, the 0 flag was not set. BEQ is branch if equal, so that's where we're doing the reverse of that. So basically if the 0 flag is set, that's when we'll take the branch, that's when we'll take the jump. Next comes up is branch carry set. So basically if the carry flag is set, we'll take the jump. And then next we've got branch minus. So again, a minus number, if we're doing 2's complement, is signified by the leftmost bit being set. So basically if the ALU operation had the leftmost bit set, it'll set the sign flag, and that's what we're jumping on here. So we're jumping if the sign is set. The next one actually is a synonym for BMI. So this is branch less than. So again, if the number's minus, it's less than 0. And that's what we're saying here. So again, we can use BMI or BLT. They're the exact same opcode in both cases. The last one then is BLE, is branch less than or equal. So again, here we're saying we're going to branch if it's the sign is set or if the 0 is set. Here's a railroad for each of those, and here's some examples of them in use. So you can see here we're just showing which flags will be used. So the first one, the not 0 flag, would be the thing that will cause the jump, then the 0 flag, the carry flag, sign for the next two, and then the last one is sign or 0. And again, you can see there at the end of each one of those lines where the opcode is, you can see which flags are actually being set in each of those cases. Now this does mean there are some other branching operations we could do here that we can't actually reach currently from our assembly language. And what we could do is create more branching mnemonics to do that for us, or I do have a trick up my sleeve which I'll introduce shortly. So there we go, add that to the list on the right. Now there is only one more thing we can do with the goto instruction, and that's basically a derivative where we load a value into one of the registers, so into the M or J register, but we never take the jump. And effectively this is a 16-bit load immediate. Now actually we've kind of already got a mnemonic that covers this, the load immediate. So what we can do is rather than create a new mnemonic for this, we can just extend the one we've already got. And that would look like this. So now you can see if we specify A or B after the LDI, it's an 8-bit load immediate that we're doing, and we're loading a value between -16 and 15. If we follow the LDI with an M or J, then it must be a 16-bit load immediate that we want, and now we're going to have to give it a 16-bit value, either in hex, or what's interesting is we can give it a label. And that's quite useful because a label actually is just the location of a line in the program, but it could also be later on in the program an area of data. So imagine we had a list of values in memory. You could treat that as an array of values. So the idea is there's a value in consecutive locations in memory. So what we could do is we could load the address of the first one of those into, say, the M register, and then we could just keep incrementing that value. So it just then points to the next value in memory and then keeps going through. And that way we could loop through a list of values in memory. I'll no doubt do an example of that in the programming at some point so you can see how that works. But here's some examples anyway of the 16-bit load immediate. And in the first one you can see we're just loading a literal hex value into memory. The one after we're loading the location of a label into memory. And the last one then we're just loading, again, a literal value into register J. So you can see for each one of those that the opcode in each case specifies just basically whether it's 110 to load it into M and taking no action, or it's loading into J with 111, and then all zeros after that to say again no action. What's really important here again is that all these need to be followed then by the value. So that LDI M at the first example there, that FE is then stored in the next 8 bits of memory, and the DC is stored in the 8 bits following that. Right, so I did say I had a trick up my sleeve for getting at some of those operations that we don't have mnemonics for. So in this case, there are some of the more esoteric branching operations that there is no mnemonic for, normally wouldn't be able to get at them. Now, I'm not sure how many assembly languages have this feature. I doubt it's something I've invented because assembly's been around a very long time, so it's highly unlikely I'm the first to do this. But I don't think I've seen an example of it. I'm sure you can tell me in the comments if there is, though. And basically, it's a mnemonic to do an opcode. So it takes the form of OPC for opcode and then a straight value. Railroad-wise, it looks like this. So you can either provide a hex opcode from 00 to FF, or you can do it in binary. And some worked examples look like this. Now these are probably quite kooky examples here because if you want to move a value from B into D, you'd do it using the mov instruction. You wouldn't do it this way. But this just shows that you actually can. The second one there is an example of doing an ALU operation. So we're doing an add, adding B and C together and putting it into A. But here we've chosen to represent this in hex. Following that, we've got a set AB instruction and then a version of goto. Now again, goto would have to be careful here because the opcode will basically just write a single 8-bit value into memory at that location in the program. Now of course goto is then going to load the next two 8-bit values into the M or J register. So here we'd have to follow that with another two opcode instructions. Otherwise you'd start writing your next instruction into the wrong place in memory and the whole program get confused. So basically by using this particular mnemonic, you can create havoc if you do forget to add the extra two values for a goto type instruction. But anyway, it's there just in case it's ever needed. And there we go, we've added it to the table. So that is all the opcodes for everything that the computer can do so far. And now what I did do though in my last video was I did touch on all the other opcodes that will be available and that I will be adding to the computer later on. And here they are. So at the top we've got the two load and store operations which take 12 cycles. That's for loading and storing values between memory and the registers. We then have the increment XY register, which is a 14 cycle operation. Then the move 16s at 10, and then miscellaneous, which is a collection of various operations. So these will have mnemonics for them eventually when they're implemented in the computer. The load and store will have LDR and STR for load register and store register. Load will take a destination and store will take a source register. So they'll both map directly to that, and that will add a little bit more to our chart. You can see at the bottom right here, I'm just putting them in grey because they're not available just yet, but they will be coming quite soon. Next, increment XY is just IXY, and actually it won't take any parameters because, well, you're incrementing the XY register, and that's it. Move 16, now again, we're going to reuse the mov command here. All that will change now is we'll just be using 16-bit registers as destination and source. And again, this is where we'll get our return command, where if we load the program counter from the XY register, effectively restoring that address that we saved before taking a jump. Now again, for convenience, we'll put a synonym in for this, and we'll call it RTS for return from subroutine. On the mix side of things, there's probably just a few instructions probably to go first of all. This is a place where we might get a few additional instructions as time goes on. I haven't quite decided what we're going to add here yet. And you can see there's 3 bits there, so in theory we could do up to 8 different things here with the MISC instruction. But the two we're definitely going to need is the halt instructions, because at the moment there's no way of stopping the computer when it's finished doing what you want it to do. So the HLT, halt, will halt the computer and that's it. HLR will halt the computer and load the program counter back with 0, or I think the way it'll probably end up working is it'll load the program counter based on whatever the switches on the front of the computer are set to. The general entry switches. Speaking of the general entry switches, that'll also give us another operation which is load switches, and that'll basically load whatever values on those front switches into a destination register. And that'll be quite useful if you want the user to interact with the computer. So you could say halt and wait for the user to give you an input. They'll set those switches, set the computer going again, and it'll carry on where it left off. Obviously that only works if you use the halt instruction, not the halt and reload. So you can see then on the right now we've got our full table of assembly mnemonics, and that's basically everything that I'm planning so far to have in my assembly language. Now just one thing I just want to return to is in my last video we had a quick look at the opcode space, as it were. So along the top there we've got a number representing the lower 4 bits of the opcode, and down the left as rows we've got the upper 4 bits of the opcode. So as before, you can see that the first 4 rows are basically occupied by the move 8 class of instruction, then the next 4 by set AB, and the bottom 4 are used up by goto, and everything else just needs to squeeze into what's left. And now what I can do is, because pretty much every mnemonic has a direct opcode equivalent, we can actually make this diagram a little bit more detailed by basically breaking this down to each of the mnemonics of the assembly language. Now if we take a look at rows 4 through to 7, we can see that the load immediate is all there. So basically either we're loading A or we're loading B, and we need all this space to be able to put in the values between 0 and 15 and minus 16 up to minus 1. Now looking up at rows 0 through to 3 at the top, we can see that we're not using up all the space at the moment, but that's because we can only do registers A, B, C and D at the moment. Now eventually you'll be able to move between all 8 of the general purpose registers, so that'll include M1, M2 and X and Y. You can probably see here then that'll give you the full permutation of 8 registers, and that'll then use up all that space at the top. So that's the upper half of that table covered. So how about the bottom quarter there for the branching instructions? There's not a great deal of space being taken up there, even though we've listed pretty much all the branching instructions that we're going to include here. And now this is because this is the way that the permutations of the various bits work. Now, if you look at the circled examples, what we're actually looking at here is if you take, for example, column 9, row E, that circle there is actually a slight derivative of the branch carry set to the left of it. And now bearing in mind, because the last bit of the opcode is whether or not we want to store the next instruction address into the XY register, effectively for doing subroutines, this is basically a do a subroutine if carry set. Now we don't have a mnemonic for that, but that's basically what it represents. And now again, this is where we could use the OPC mnemonic to be able to call this directly if we ever wanted to, or we could just wire it out by using a collection of different mnemonics to achieve the same effect. So carrying on that same theme, you can see that in column 5, to the right of BEQ, that will be subroutine if equal, and the one below it will be subroutine if less than or equal. Now later on I may choose to add some mnemonics for these, but I couldn't really find any nice ones that fitted, and what I didn't want to do is add too many mnemonics and try and complicate the language any more than it already is. Also of note is these circled items here. And now these are actually all the same as the jump at row E, column 6. And this is because if you look at row E, column E, then the value there is basically saying jump if equal, not equal, or the carry is set. Now in this case, it's always going to be equal or not equal, so it's always going to jump regardless. So this is basically just a repeat command here. So if we did have a mnemonic here, it would be JMP. Now the same applies here if you look onto row F, column 6. This would be a jump if the sign is set, or it's equal, or it's not equal. And finally on the last row F and column E, this one will be jump if sign is set, carry is set, equal is set, or not equal is set. Either way, it's just a jump again. It's always going to take the jump. Right, so that's pretty much everything covered off on the assembly mnemonics. So just to round off, here's some of the railroad diagrams that we've introduced so far. So just to finish off then, in my last video I introduced the Relay Computer Simulator. Now this time I'm going to introduce the editor. So this is actually a little online IDE that will just allow you to actually write programs in the assembly language. Now it has things like syntax highlighting, so you can see it's colouring all the values there, and also it will tell you if anything's syntactically incorrect as well, so it will squiggle any items that aren't correct or aren't known opcodes. So it's there to have a play with. Go to editor.relaycomputer.co.uk and you can have a play with that. Also, if you want to see those railroad diagrams in another form, you can get them at relaycomputer.co.uk/pages/assembly.html. Right, so that about wraps things up for this video. So in the next video, I'll be looking at actually writing a program for the computer. What I'll do is do an example of running the Fibonacci sequence. So what I'll do is I'll take it through the initial idea, basically then converting all that into pseudocode, and then working out then how to actually operate it on the computer. And what we'll do is we'll start from the assembly language, we'll then convert that by hand into the binary opcodes, and then load it into the simulator and show it running. Now, of course, eventually I'll show a demo of that actually working on the real computer, but that'll come in the last video. In the meanwhile, thank you for watching, and as before, if you have any comments or questions, please do pop them in below. Otherwise, I'll see you on the next video.